Let's do a tough telescoping series example. There's easier ones you can study in your notes and in the textbook. Here it is. We notice that the denominator can be factored. We're going to take this fraction and decompose it using partial fraction decomposition. Let's eliminate the denominators by multiplying by the least common multiple of the denominators. Multiply that times the left side, and we'll have 12 remaining. Multiply it times the right side, and we'll have to use the distributive property. When you multiply it by the first term, the n plus 2 in the denominator will cancel out with this n plus 2, leaving us with a times n minus 2. And when you multiply it by the right term, we're left with b times n plus 2. Next, we need to find out what a and b is. That's the whole point. What is this fraction? What are the numerators? So to do that, we will let n equal positive 2, and then we'll let n equal negative 2. Why? Because that will force one or the other of these terms to cancel out. For example, when n is equal to positive 2, we'll have 12 equals a times 0 plus b times 4. So it's really easy to see that b is 3. And when n is equal to negative 2, we'll have 12 equals a times negative 4 plus 0. So it's really easy to see there that a is equal to negative 3. All right, let's rewrite our series now that we know how this fraction can be decomposed. This series can be rewritten as the sum as n goes from 3 to infinity of a over n plus 2 plus b over n minus 2. Put that in parentheses. Rewriting this is not necessary, but I'm just putting the positive term in front, subtracting the other term. All right, next, expand. All right, so letting n equal the lowest index, 3, we have this fraction, and then when n is 4. And then when n is 5, 6, 7, 8, this is an infinite series, but let's just stop for a second. Let's see if we can notice things that are canceling out right now. I see this negative 3/5 and positive 3/5 cancel out. Negative 3/6 and positive 3/6 cancels out. Negative 3/7. I'm not seeing the 3/7, but I know that the next first term is going to be 3/5, 3/6, 3/7. But if we stopped at n equals 8, nothing else cancels out. Not the 3/7, not the 3/8, not the 3/9, not the 3/10. So if we stopped with n equal 8, then only 2 pairs cross off, and we're left with 3 and 3/2 and 3/3 minus 3/7 plus 3/4 minus 3/8 minus 3/9 minus 3/10. What if we actually let n go up to 10? Then what would cancel out? Now we can see this negative 3/7 cancels out with the positive 3/7, and this negative 3/8 cancels out with this 3/8, leaving us with the positive, 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 and positive value, and then minus the negative, 3/9, 10s, 11s, and 12s. At this stage, I'm wondering if these 4 remain and we always have 4 terms that don't get crossed off. Let's do this one more time. All right, if we go out from n equals 3 to n equals 12, we add on these other terms, and some more things cross off. So let's see, minus 3/9 cancel off with positive 3/9, and one more, the negative 3/10 cancels out with the positive 3/10. So what are we left with at that stage? Well, we're left with the same 3 as before, the same 3/2 as before, the same 1 as before, the same 3/4 as before. But now instead of starting with minus 3/9, what's left was minus 3/11, minus 3/12, minus 3/13, and minus 3/14. So we've established a pattern that we can be very confident is correct at this stage. Our nth partial sum will always be 3 plus 3/2 plus 3/3 plus 3/4, and then it will always have 4 negative terms. and it will always be, when n was 12, we started with 1 less than that, and then n itself, and then 1 plus n, and then 2 plus n. When n was 10, we started with 1 less than that, and then n itself, and then 1 more than that, and then 2 more than that. So this is the expression for the nth sum. And if we take the limit as n approaches infinity of both sides, these terms go to 0. So the limit of our series, it converges to the green parts, which is 3, 4.5, 5.5, 6.25. And the lesson to be learned from this telescoping series problem: don't expect to always be able to discern the pattern from just a couple of terms. You might have to expand a bunch before you can confidently deduce what's being crossed off and what the pattern is. All right, the bouncing ball problem. A-Day class, you don't need to watch this video. You can skip it. Well, you're pretty much done, because example 3 will be a repeating decimal problem, and A-Day saw that. B-Day class, you haven't seen one of these, so I'm going to present this problem, and then you should probably stop the video and give it a try. And then I'm going to present one possible solution, and by the end, you should feel pretty confident with dropped ball problems. So this ball is dropped from 120 feet, and when it bounces back up, it will bounce back 80% to where it previously fell. How far will it have traveled by the time it is at rest? Go ahead and stop the video and give it a try. All right, in 5 seconds, I'm going to work through the solution. All right, there's many ways to represent this, but a really nice way is to represent the drop there as 120 feet. And then it bounces up 80% of the way, and then it'll fall at the exact same distance. So we'll have 2 of those distances. And then from there, it will bounce up 80% of the way, and then fall back down. So we'll have 2 of those distances. And it just keeps this up. It'll bounce up 80% of the way, and then fall back down. So we'll have 2 of those distances. So let's go ahead and represent what these distances are. First fall was 80% of 120. So let's write that out. 120 times 80%. You don't need the 0, so I'll stop there. The blue distance is 80% of the previous fall. So what is 80% of this number? We're just talking about inside the brackets. So that's going to be what that number was. But we have to take 80% of that. So when you multiply that by 80%, we will be raising that to the second power. And then the black distance will be the blue distance, which is 120 times 80% to the second power, but we have to multiply that by 80%, so that's going to be to the third power. We have our series. So to calculate how far this ball travels by the time it's at rest, we have a series where we can recognize that it's geometric, and you just have to be careful about how you do this. There's more than one ways of doing it in terms of factoring, and so I'm just going to show one possible way. It's not the only way. It's not necessarily the best way. Since every one of these terms, except for the green one, has a factor of 2, I'm going to leave the green one out, and it's not going to be part of my series. For what remains, every single term has a factor of 2, so I'm going to factor that 2 out. Also, every single term has a factor of 120. So just using algebra 1, the distributive property, I'm going to factor out the 120. What remains will be our series, which was 0.8 plus 0.8 squared and onward. A nice, simple geometric series. So the total distance that this ball travels is 120 plus 240 times a geometric series where the absolute value of r is 0.8, and that's less than 1. So it converges to the first term. You can see it right there in blue, over 1 minus the common ratio. And there it is. Total distance this ball traveled is 120 plus 240 times 8/10 divided by 1 minus 0.8, which is 0.2 or 2/10. So we have 120 plus 240 times 4. Or 1,080 feet, if I did that mental math correct. All right, that's how you might do a bouncing ball problem. I expect 100% of you to get this problem correct if you ever face it on an exam. All right, for the last example, we're going to show how to write a repeating decimal as a fraction using series. All right, suppose we were asked to write this value as a fraction. Let's first represent it so that part of its representation is a geometric series, and then we'll go from there. If we start with this first block, or the set of decimals that contains the first block of 219, we can rewrite that as 219 tenths, hundreds, thousands, 10,000s, 100,000s. And then to get the next block, which I'm going to do in blue, how much is that? That's 0.0000219. Right? 1, 2, 3, 4, 5 decimal places, and then this block of 219. 1, 2, 3, 4, 5, 219. Well, what is that decimal? That decimal is the tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. So that's 219 over 100 million. So if we think of that in terms of a fraction, that's 219. The question is, what did this denominator get multiplied? It currently has 5 zeros. Here it has 8 zeros. So it must have been multiplied by 1,000. This previous term gets multiplied by 1 over 1,000. That will give us 219, and then 100,000 times 1,000 is 100 million. 5 zeros and 3 zeros gets us 8 zeros, which is what we had. Well, if you go to the next block, we move 3 decimal places over, which is why we are multiplying by 1,000s. So for the next term, we'll have 219 100,000s times 1,000th times another 1,000s. So in other words, and now it's pretty clear what our geometric series is. So we have 17 plus. So here's our geometric series. The first term was 219 100,000s. And then 1 minus the common ratio, and the common ratio is 1 1,000th. So we'll do 1 1,000th. So this is 17 plus 219 100,000s. And then this denominator will be 1,000 thousandths minus 1, so 999 thousandths. So our final answer, 17 and 219 999ths. If you've learned those repeating fraction things with, it's always divided by 9 or 99 or 990 sometimes, then there's easier ways to do it when you know the pattern. But this was practicing writing a repeating decimal as a geometric series and then using our knowledge about geometric series to come up with a fraction. That's it for these examples. Have fun with the homework. There's 16 questions. Get her done. Have a great weekend, everybody. Or if you're an A-Day student, I'll see you tomorrow.